Alright, now we can start. Okay, so today we are going to cover chapter 3 in fluid mechanics. It's a finite control volume analysis, part 1. So I divided the chapter 3 in 3 parts. Okay, so today we will cover part 1 and some of part 2. Okay, and next class we continue some of part 2, and next week we're going to cover part 3. So we'll be using 2 weeks 2 weeks to complete the chapter 3. Okay, but next week you are having a semester break, and so we'll continue after you coming back. Okay, so before this you have cover chapter 1 and 2, mostly covering the fluid static and fluid static. So in chapter 3 is mostly cover the fluid dynamics. So what's the difference? Static and dynamic. Dynamic is moving. Okay, the fluid, your fluid is moving, but in static, your fluid is static lah. Okay, so that's the main difference. So in chapter 3, so there are 3 subchapter. Okay, so we have introduction to fluid flow. So we're going to see this today. Okay, and some little bit briefly on Eulerian and Lagrangian description of flow. Okay, we cover today. And visualization of fluid flow ni I think we cover next class. Okay, and today we also will looking on continuity equation. Okay, and some of Bernoulli equation. Okay, so that's for today class. Okay, alright. Okay, before to do you want to ask anything about chapter 2 on the quiz, or chapter 1? Any macam tak faham apa? Do you want me to repeat it again or whatever?
Okay, so okay. Tapi saya untuk quiz tu ada berapa soalan
Alamak, saya tak sure Pak. Adalah beberapa soalan. I'm not sure the exact numbers, but few question.
Okay.
Okay. I don't think that's a matter. But yeah, the few question. If you want to know, I will check after this. I will let you know lah berapa question. Okay. But anything about the topic, whether you not still not understand how you find the FR ke kan, on the curve or on the plane before we go to this chapter, because you're going to have the test tomorrow kan?
Yes, sir.
Ada apa-apa before saya pergi chapter baru ni?
I think no, sir.
Okay. Okay, just if you have any question, just raise it up. So maybe after we have finished this chapter 3, for today's class, we can discuss a few. Okay, coming back to chapter 3. Okay, introduction to fluid flow. Okay, my pen is working. Okay, so there are 4 different flows. So if you read from this description, okay, you can read and memorize and understand like the clip. So you can say the cross-section area and velocity of the stream may vary from cross-section but for each cross-section they do not change with time. Example, okay, you can do that, okay, as well. But the most important thing is you need to understand, okay, what is different between steady flow, uniform flow, laminar flow, and turbulent flow. Okay, so if in exam they ask you the definition, you need to answer like this. But bear in mind, the most important thing is you need to understand. Okay, the steady flow. Okay, we look for steady flow first. So its definition is the cross-sectional area and velocity of the stream may vary from cross-section, but for each cross-section they do not change with time. So the key word here you need to understand is the steady flow, they don't change with time. Okay, so the delta T tak adalah kosong. Okay, For example, a wave traveling along a channel. And so if you have a flow, okay, the steady flow, okay, any the cross section here, okay, the velocity not change with time. Okay, so that's the definition of steady flow lah. Okay, if you example, they give you example here, a wave traveling along a channel. So second one is uniform flow. Okay, so definition of it, the cross sectional area and velocity of the stream of fluid are the same at each successive cross section. Maksudnya dari kat sini ke, kat mana-mana ke, okay, any cross section, okay, are the same. Okay, are the same. Okay, tadi tu dia maybe one kat sini je yang ni kan, tak change with time. But in uniform flow, every cross section, okay, there is on constant. The velocity, the cross section area is the same. For example, the flow through a pipe of uniform bore running completely full. Whenever you open your pipe, okay, at a similar velocity, okay, the fluid inside flow, so kat sini sama kat sini, sama kat sini, sama ni, semua sama. So that's a uniform flow lah. Okay, you don't put any external force or any external pressure. So you just open one inlet and let the flow through the pipe. Okay, that's uniform flow. The third one is laminar flow. Okay, also known as streamline or viscous flow, in which the particles of the fluid move in an orderly manner, okay, and retain the same relative position in successive cross section. Okay, in a flow, okay, for laminar flow, so the fluid, that fluid ni dia ada layer lah, the layer, okay. So that layer, this layer of the flow is in a very orderly manner. Dia tak collide with each other. One layer ni satu. Dia smooth je lah. Okay, they not collide with each other layer. Okay, so that's laminar flow. But for turbulent flow, so the opposite of laminar is turbulent flow, where you have the particle of the fluid, okay, inside this flow. Okay, let's say ada banyak particle. So this particle collide with each other. Dia boleh bertembung-tembung. Okay, dia langgar-langgar, and that's if you see in the real world, it will create turbulence lah. Ada turbulence, ada turbulence sebab dia langgar-langgar kan. That's why we call it the turbulent flow, because the particles of the fluid move in this orderly manner. Okay. Normally, if you have a very high flow rate, okay, of fluid, then it will create a turbulence, kan? So normally higher velocity of fluid normally represent the turbulent flow lah. Okay, you will learn it in depth before, in depth after I'm not sure. I think not in this topic. In the future maybe. So the number that will differentiate whether it's turbulent or laminar is what we call it is Reynolds number. Reynolds number. So this Reynolds number will tell you whether the fluid is Reynolds ILD, whether the fluid is turbulent or laminar. Okay, so this briefly introduction to fluid flow. Okay, the next is we have two different method or approach whenever we want to analyze the fluid moving in a system. Okay, one is we call it Lagrangian. It's based on ada nama seorang lah, mathematician, nama dia apa saya tak ingat lah. So that name is come from his name lah. So this Lagrangian method ni come from one professor's name. So he create this method. And another one is Eulerian method. Okay, so this also a name of a person, Eulerian something, I'm not sure, I don't remember. It's not important. Okay, so these two different methods will help you to analyze any fluid flow, right, in any system. Okay, so what is the difference between Lagrangian and Eulerian. Okay. To understand what is the difference between Lagrangian and Eulerian, one you need to you have to understand the fundamental but to get it simple in simplest way, okay. If let's say there is a so let's say this is you, okay, I don't know whoever he is, okay, and he is sitting beside a river, okay, this is a river, okay, I'm sorry for my drawing, it's not too nice, okay, and this person want to measure the velocity of the flow inside this river, okay, this river, sungai Kim ke apa, I'm not sure, okay. So there are two types of approach, different approach. The first one is Lagrangian, okay. Whenever he want to use this method, Lagrangian okay, what he will do is he will put a probe ni instrument along this river, okay. He will float the probe and measure all the way sampai habis sungai tu kat mana kan, and this probe will record the velocity of the fluid along the river, okay, because it use Lagrangian ni, they will measure the whole thing, okay, the whole thing but if he or she use a Eulerian method, he will just put a probe at one position, okay, and measure it there, measure kat sini je, okay. He will measure the velocity of the flow, whatever, dekat at this point, okay. So that's the difference between Eulerian and Lagrangian in bird view eye lah, okay. How you want to understand the difference between Lagrangian and Eulerian, okay. Eulerian will take one finite space or volume and measure it there, okay. Kat sini kalau yang ni dia letak sampai kat sini je lah dia measure and Lagrangian they will measure the whole river, they will float the probe whatever he use and let it flow sampai habis, and then he will record from there lah, and he will see what's the velocity of the flow, the water flowing in the river, whatever. So that's the main difference. That's why he said here, the Lagrangian approach ni will follow the path of individual objects, okay. So, in this case, the water in the river ni, it will follow all the way, okay. Dalam contoh ni dia bagi ball, dia bagi a pool table collide with another ball, ada bola and they collide, and then it will follow lah whichever this ball whether it move over there or move over there, so it will record the velocity, the momentum, okay, based on the whole individual object, okay. So that's Lagrangian method. But for Eulerian, he will just we will describe dulu finite volume or space, and then we use that space or that volume to find the variable speed ke apa-apa ke dekat at that point, okay. So that's the difference between Lagrangian and Eulerian, okay. So I don't want to explain more on this word. I think if you understand that, again, that's the concept, then you understand lah why different between Lagrangian and Eulerian. Okay, mostly in a fluid flow, okay, because it is a fluid, okay, you cannot simply use Lagrangian method, kan. Kalau Lagrangian method ni, kata kalau dia guna untuk bola kan, is simple and is doable to use Lagrangian method if you want just to analyze like a very solid object, kan, a ball collide with another ball, and you see where it's moving, because it's just a solid ball, kan. But in a fluid flow, there are a lot of particles inside a fluid flow, kan. Ada banyak molekul-molekul air, kan. Okay, so you cannot see any individual molecule of the water kan, of the fluid kan, whether collide dengan molekul lain ke apa, it's very difficult, it's very susah lah. Okay, that's why commonly used in fluid flow we use Eulerian. Okay, because we can define our finite volume, okay, finite space, and we measure it inside this finite space or finite volume. Okay, we can measure the velocity of this water molecule here. So it's simple lah, it's simple and can be can be tracked, can be measured. Okay, that's why you have two different approach and different application lah. So Eulerian mostly we use in a fluid flow. Okay, macam ni lah. Okay, this is a fluid flow. So you define your control volume, and in this control volume you can find your velocity in x direction and y direction or z direction with time, kan? And you can find the pressure of the fluid flow in x direction, y direction or z direction with respect to time. So this is most applicable lah to analyze any fluid flow. We will using the Eulerian approach. Okay, so that's the difference lah between Lagrangian and Eulerian. Okay, so that's basic theory. Okay, now we go to fluid flow ni. Okay, fluid flow. So before, like I said before this, when you learn chapter 1 and chapter 2, mostly you are covering fluid static and the fluid is not moving. So in this case, in this chapter, so you are analyzing the fluid flow, which will we call it the fluid dynamic lah. The fluid is moving kan. So you have dynamics and the velocity. So normally what we are interested with is the velocity and velocity of the fluid, and we are interested in the pressure. Okay, the pressure of the flow. Whereas we interested in elevation. Okay, elevation. Okay, how high or how low the fluid is moving, whether it goes up or goes down. So we interested to find it. Okay, so in this fluid dynamics, okay, so we are these three main parameters we always try to find lah. Okay, so normally, okay, in chapter 3, most people also call it as Bernoulli equation. Okay, Bernoulli, I think Bernoulli equation. Okay, I think we have learned it before in have you learned it in secondary school? Ada ke? Tak dengar?
Bernoulli ke sir?
Bernoulli.
Ada
kan?
Form 5.
Form 5. So that's I think it's very common lah. It's not alien word pun kan. I think all of us have heard this Bernoulli equation because we have learned it in the secondary school kan. Okay, so what are the laws that we are going to use in this equation? Okay, so there are three. Okay, there are three laws that we will use or depend. Three different physical laws. Okay, there. Physical laws. Okay, the first one is the law of conservation of mass. Okay, if you have a difficulty to read my handwriting, you can refer to the notes. I have posted the notes in part 1. So in the notes they will also telling you the same thing lah. So I just want to use like this, so it's more interacting lah. So the first law is law of conservation of mass, okay, and the second law is the Newton second law. Okay, I think you know this one as well in school. Okay, and the last one is the first law of thermodynamics. Okay, so these three laws we will be using in this chapter lah. Okay, so there must be a equation, different equation for all of these laws. The first one, the law of conservation of mass. So this is what we call it as continuity equation. Okay, the Newton's second law, we call it as momentum equation. Okay, momentum equation. And the first law of thermodynamics, this will be your energy equation. And what is this equation does? Okay, it will balance some of the property lah. Okay, for the first one, it will balance the mass. Okay, and the second one, the Newton's second law, the momentum, it will balance the momentum. Okay, and the last one will balance the energy lah, as the names tell you. So it will balance the energy for any two location, any 2 points. Okay, using this energy equation. Okay, so like for example, what does this mean by balance? Okay, if you have a pipe, okay, I'll just draw a pipe. So at this point 1 and point 2. Okay, so using these different physical laws, okay, so the first one, it says that the law of conservation of mass, and the mass is balanced. That means the mass at point 1 is equal to the mass at point 2. Okay, and the second one is Newton's second law. It tells you about the momentum. So the momentum at point 2, let's say momentum is F, also the same at point 1 will be the same at point 2. Okay, and similarly for energy, okay, energy will be the same at point 1, will be the same at point 2. So that means by what is if you say balance ni, that what it means lah. Okay, it balance at 2 different point in this pipe. Okay, so we will going to see first the law of conservation of mass, okay, and the first law of thermodynamics with energy. Okay, this one, the Newton's second law, this will be in the next class. Okay, today we are going to learn about mass and energy. Alright, okay, we go to the next slide, conservation of mass. Okay, so there are 3 parameters whenever you talk about conservation of mass. Okay, 3 parameters that is very important. Okay, the first one is what we call it as Q. Okay, this is volume flow rate. Volume flow rate. Okay, so the unit is, the volume is meter cube, meter cube. Flow rate, that means it's per time lah. You calculate the rate, it's kadar, so it must be over time. Okay, so time is per second. So this is the unit for volume flow rate, volume meter cube over second, because you find the rate. And the equation is for Q is A the area times V, okay, the velocity. Okay, the area you will have the unit is meter squared and the velocity is meter per second. Okay, when you multiply the area with velocity, then it will give you meter cube, meter times meter square and meter cube over time. Okay, so that's the first parameters you need to understand. First, volume flow rate. The second one is m dot. Okay, this is mass flow rate. Okay, mass flow rate. Okay, the mass, you know, mass is in kg. Okay, so the unit is kg. The rate, similarly, rate must be over time per second. Okay, and the formula for mass flow rate is rho, the density, times q. Q yang atas ni lah yang volume flow rate. Or you can write it in another question, because q is similar is equivalent to A times V. So that means you can write your mass flow rate in rho times A, the area, and times V, the velocity. Okay, so if you so this is density, density. So this is density mass over volume, so mass kilogram over meter cube. So if you times q, okay, you can cancel out the meter cube, and then it will give you kilogram over second. Okay, or you can change your q in terms of area and velocity. Okay, the last parameters in this conservation of mass, conservation of mass is W dot. Okay, it is the weight flow rate. Okay, so the unit is, you know, weight. Weight is Newton kan. Weight W equals to M times G kan. So or the unit is Newton. Okay, so it's Newton. Similarly, it's flow rate, so it's per second per time, per unit time, so per second. Okay, and the equation for weight flow rate is just a multiplication of G, of the mass flow rate. That means rho G Q. Okay, different is just you multiply by G, you will get your weight, mass flow rate. Because you know mass, to get to weight, you times G, W equal to mg. So that's why in this the third parameter as well, the weight flow rate, you just multiply by G, 9.81, and you will have your weight flow rate. Or you can write it as you know, the rho G is equal to your specific weight n, gamma. Okay, gamma Q. Okay, if they get you specific weight, that means your rho G. Or you can also change this Q in terms of rho AV, and that means your this equation will be the rho G A V N. Okay, so that is weight flow rate. Okay, I think it's quite simple. It's just a volume equation, volume flow rate, mass flow rate, and weight flow rate. Okay, for example, I give you an example in the same study, in the same part tadi tu. Okay, let's say there are 1 point here, 1 and point 2. Okay, and as the principle of continuity, so all these parameters will be the same at point 1 and point 2, and whether it is volume flow rate, Q1 is equal to Q2, or whether it's a mass flow rate, m dot 1 equal to m dot 2, or is it weight flow rate, so w dot 1 and w dot 2. Okay, so that's the principle of continuity lah. Okay, this volume flow rate, mass flow rate and weight flow rate is equal to is equal at point 1 and point 2, and this will if you take one parameters, let's say volume flow rate, so that means you can translate it in the area 1, okay, the area for at point 1 times the velocity at point 1 is equal to the area at point 2 times the velocity of point 2 sorry 2. Okay, so that's how you the problem will ask you. They will give you the area of this point, the velocity of this point, and they want to ask you to find what's the velocity at point 2 and given the area of 2. Okay, so that's how commonly asked in test or in question. Okay, they just want we find, so what's the velocity here, or what's the area here. Okay, so that's inilah okay, so any question before we go further? Okay, and this equation is valid for all fluid, valid for all fluid, whether it is gas or liquid. Okay, so that is first. Okay, conservation of mass, how you can find this volume flow rate, mass flow rate or weight flow rate given if you have the problem. They will give you the area for one. Okay, let's say the area for one is we see one example so that we can have a clear understanding. So they give you the area of one is what's number, let's say 0.05 and they give you the velocity at 1 at 1 is berapa, any numbers, 10, okay, 10 meter per second, and they give you the area at 2. Okay, this is smaller so let's say it's 0.2 lah. Okay, 0.2, and they ask you to find what is the velocity at point 2, so you just use this formula, so you know the volume flow rate is equal at point 1 and point 2. So you have your A1, you have your V1, and you have your A2, so you can find your V2 lah. So V2 is equal to A1 times V1 over A2, and if you put the numbers, your V2 should be higher than V1. Okay, because this is very the area is reducing, that means your V must increase if you can check, the area is 0.05 times V 1 is 10, divided by area at 2 0.02, and this will be give you velocity 2 at point 2 is 25 meter per second. If you can realize the velocity at point 1 is only 10, but whenever it flows through this pipe, because it's smaller pipe, the velocity is higher. Ini contoh macam kamu siram air siram bunga you want to to make the flow higher, you press the pipe you make the pipe smaller so whenever you make the pipe smaller, then the area of that point 2 is smaller, then you will have a very you will increase the velocity so ni contohnya lah that's how is why the theory behind so lepas ni kalau awak ada siram bunga tolong mak ayah siram bunga, you know this conservation of mass, and you can tell your dad or mom, look, this is conservation of mass, the volume flow rate here is equal to A area times V, and I'm not sure whether your mom or dad will understand, but that's it, that's the understanding lah. Okay, So that's the first equation, which is the conservation of mass. Okay, where we balance the mass. And so the mass, when we talk about the mass, there are three parameters: the volume flow rate, mass flow rate, and weight flow rate. Okay, can we move forward? Now is one. Okay, next one. Ada soalan ke? Tak ada. Okay, next one, we go to conservation of energy. I told you for today's lecture, we will cover the conservation of mass and the first law of thermodynamics, the energy equation. Okay, who can tell me the first law of thermodynamics? You have learned it before. Have you learned it before in school? Ke tak ada?
Tak ada, saya tak ada.
Oh, tak ada. Sorry. Jangan ada. Conservation of energy. Okay. There are three things that you need to understand. Okay. The first thing is the energy. Any energy cannot be destroyed. Can't be destroyed. Okay. Dia tak boleh musnah. Any source of energy, you cannot destroy it. It will only, okay, energy needs only first whether it's transferred. Okay, it can transfer from one point to another point. Okay, let's say another point. Okay, you can transfer the energy, or you can transform the energy. Okay, let's say from any kinetic energy, this moving energy, you can transform that kinetic energy to electrical energy. You can transform chemical energy from a battery to the electrical energy. Whenever you use in your phone or kipas ke calculator ke, so the energy from this battery, the chemical energy, is transformed to the electrical energy. So that's the three things that you need to remember to understand. Energy ni cannot be destroyed, but it can transfer from one point to another point and transform from one type of energy to another type of energy. So that's the conservation of energy lah. Okay, I think it's quite basic. And for example, you want to transfer a point, let's say you in higher location. Let's say you live in an apartment. Okay, let's say apartment. So you are living in level 5 or 4. Okay, and then you throw any weight or any object downwards. So they will there is a energy transform here, and transferred from one point to another point. And if you dalam ni ada MGH kan. Okay, the potential energy is regarding the height, the elevation. So whenever you drop, so there's a potential energy being transformed. Okay, that's an example. Okay, so there are three types of energy, as I mentioned here. This is one. Okay, one is potential energy. Ni tadi lah potential energy. Potential energy. Allah, kita padam pula. Sorry. Okay, three types of energy. Tadi. The first one is potential energy. Okay, potential energy, or we can call it as PE. Okay, stands for potential energy, and this is equal to the formula for potential energy is WZ. What is W? W is weight, okay, and Z is elevation. Okay, that's why we talk about here in the first slide. I think, where is it? No. Okay, here. So this elevation that we are interested is the main parameters. Okay. So in potential energy, okay, the formula for potential energy is Wz. How you get this? Wz. I think when we were secondary school, I think we always learn it as mgh, kan? Is it true? Ada tak belajar macam ni dulu?
Ada, sir.
I think I can recall lah, whenever I was in secondary school, I think we learn it mgh, kan? The potential energy regarding the height is mgh, kan? Sama je, jangan confuse dengan Wz ni. It's not a new term. It's just because mg is equal to W, kan? Mg ni sama dengan W, betul? Okay. And h ni height lah, dia punya ketinggian tu, kan? In meter, kan? So Z ni pun in this chapter they use it Z as elevation. So that's your H lah. Okay. So don't get confused. It's a similar thing with what you learn when you were in your secondary school. But before that we use mgh, and now in this chapter 3 we use it Wz. Okay, W stands for weight, or you can equal to mg, and Z is h lah. Okay, Z is Z, height or elevation. Okay, so potential energy, okay, as you know, you learned it before, it is due to elevation lah, elevation. Okay, lagi tinggi elevation awak tu, lagi banyaklah potential energy, kan? So there must be always a reference point. Where is your reference point? Okay, let's say at the bottom is your reference point 0, and if you go up, okay, this is your elevation lah, whatever meter, 2 meter or 4 meter or 10 meter. So this is your Zn. Okay, so there must be a reference point. Okay, so that's settled. I think it's quite easily understood, potential energy. The second one is also famous. We have done it before in secondary school. What we call it as kinetic energy, kan? Okay, and this is due to what? Any guess? Due to what? Kinetic energy.
Velocity.
Apa?
Velocity.
Yeah, yes, velocity, kan? So any moving object, they have a velocity, and this will create a kinetic energy, So the faster the object is moving, the higher the kinetic energy is produced. Okay, so this is what we call it as KE, KE, kinetic energy. And the formula for kinetic energy is W, okay, V squared over 2G. Okay, W is weight, again weight. The V is velocity, 2 is 2, and G the gravity, the gravitational constant. So I think before this, when you learn in school, the common equation is half mv squared. Is it true? Betul tak?
Betul, sir. Betul. Ada.
Betul, sir. Ada.
Betul. So then don't get confused. It's just the same thing. Okay, half. Ni half lah, kan? Bagi dua ni half lah. Half mv squared. Okay. So before this you use m. So in this chapter you use W over G, kan? Sama lah, W is equal to mg. Okay. So m is equal to W divided by G. So that's why you get this equation, WV squared over 2G. Okay. So it's just the same thing. You have done it before in your secondary school, half mv squared. But in this chapter you use half WV squared over G. Sama je, tak ada apa-apa yang lain pun. It's not a new term. Okay, so this is due to velocity. And the last one, okay, last one ni maybe we not heard it before. It's called a flow energy. Okay, flow energy. Okay, this might be a new term that we never encounter in secondary school. Okay, so we call it FE. Okay, FE. Okay, flow energy. And what is the equation for flow energy? Okay, it is the W, okay, the weight, P, pressure, over gamma, the specific weight. Okay, or you can the specific weight, you know, it is rho times G kan. Okay, so the equation for flow energy is weight times pressure over your specific weight. So what does it mean by flow energy? It is the amount of energy, okay, let's say this pipe, okay, this amount of energy to move from one point, okay, let's say like this, okay, to move one point to another point here. Okay, this is what we call or what defined by flow energy. Okay, the flow want to push the work from one point to another point. Okay, so it needs some energy lah to do some work kan. You know energy, work kan, whenever you want to do a work, you need energy. So this flow energy is the work done by moving one point to another point, and we can calculate it by this equation, the weight times the pressure. This is not rho, don't confuse, it's a P, okay, P, pressure over specific weight. Okay, alright, so all this energy, you know, the unit is joule lah, okay, okay, so in any system, in the fluid flow, the total energy, okay, is equal to the total energy, we call it the E total, E total, summation of these three energy lah. Okay, so you have your potential energy, plus you have your kinetic energy, plus you have your flow energy. This will give you your total energy. Okay, whenever you have similarly like your pipe tadi tu, okay, because you balance the energy, okay, at one point to second point, one point, or first point, second point. So the energy here, energy 1, E1 and E2 must be equal then. Okay, so you can find lah using this equation. Alright, so your PE, your potential energy is equal to WZ1. Okay, we refer to E1 first, the energy at point 1, okay, plus your kinetic energy, okay, you have your W V squared over 2G. Okay, the V ni V yang 1 V yang dekat point 1. Okay, and you have your flow energy, okay, W, pressure at point 1, okay, over your specific weight. Okay, this must be equal to total at point 2 lah. Okay, similar thing but different ni lah point kan. So you have your potential energy, so WZ2, so you have your WV2 squared over 2G and plus ke bawah ni, plus you have your weight times pressure 2 over specific weight. Okay, so this is the energy balance lah. Okay, that's what we call energy balance. Okay, the energy at point 1 is equal to energy at point 2. Okay, so this is lah conservation of energy lah. And because you have the similar weight, okay, the fluid have a similar weight. Okay, the W ni sama, sama. That means you can cancel out lah kan. So it have three terms at the right hand side and also 3 terms at left hand side with the same W. So you can cancel out the W. Okay, that means it will give you the last equation. Okay, because you already take out the W, and it will give you only, okay, first the the P1, okay, yang ni P1 ya, ambil yang flow energy dulu over specific weight, or you can translate it in rho g. Okay, because specific weight is equal to rho g plus, okay, plus you have your Z1, so you already cancel out the W. You have your Z1 plus you have your kinetic energy, okay, V1 squared over 2G, okay, and equal to the right hand side term. Okay, you have your P2 over rho G, and plus you have your Z2 plus you have your V2 squared over 2G. Okay, sama lah, ni sama je. I just arrange it so that the flow energy at the beginning, and then your potential energy and your kinetic energy. Okay, this equation, okay, this is what we call as Bernoulli equation. Okay, any question? Sama je ni apa kat sini ni sama je, just W, why we cancel out W if you ask, because it's the same W, the same weight, that's why we can cancel out. Kalau dia similar term, ada kat sini boleh cancel, ada kat sini boleh cancel, ada sini boleh cancel. So we remove the W, so we left to us with this term, and this term we call it Bernoulli equation. Okay, boleh?
Boleh sir.
Boleh good. Kau dah? Okay. But of course, this theory, okay, the Bernoulli equation, have some limitations. Okay, the limitations of Bernoulli equation is the first one is, I think there's also in the notes, it's only valid for okay, incompressible fluid. What does mean incompressible? It means that there is no density change. Okay, so it's the same fluid and the same density. Okay, and you cannot compress it and compress to change the density. So that's the first rule. Okay, the second rule is that there is no mechanical device, okay, between 2 points. Okay, 2 points of of interest or section lah. Okay, let's say tadi tu yang dalam pipe tu dalam contohnya dia. Okay, dia sama lah. So point 1, point 2. So between this point, okay, there's no mechanical device apa-apalah, compressor ke pump ke yang boleh tukar the velocity or pressure or whatever lah because of this device. So there's no device, only clean, tak ada apa-apa between these 2 points. Okay, so that's the second rule. Okay, the third rule is, okay, there is no heat transfer, okay, into ke dalam or outside, okay, out of the system, okay, or the fluid lah, okay. So tak ada heat masuk or heat keluar daripada sistem tu, okay. There's no heat transfer. And the last one, okay, the rule is, if you want to use this Bernoulli equation, it must don't have no energy loss. Okay, so we said that before. We balance the mass, we balance the weight, okay, we balance the volume, and we also balance the energy, and this energy balance, and using the first law of thermodynamics. So there must be no energy loss to surrounding lah, okay. For whatever reason, maybe due to friction, okay, or anything else, okay. That's the 4 rules in applying Bernoulli Bernoulli equation. But in reality, okay, practicality, in any fluid flow, okay, in a pipe, they always have a friction. Dia dengan pipe ni mesti ada friction kan? Okay, friction sini dekat along the pipe lah, along the pipe. Let's say pipe, okay, ada flow. This flow we always have this friction with the wall. Okay, akan sentiasa ada, takkan tak ada lah, mesti adanya. Okay, that means this Bernoulli equation cannot apply lah, because we have the energy loss. Okay, whenever you have the friction, okay, you have the energy loss, and this energy can be in form of heat. Okay, so you can transfer heat outside. Rule number 3 dah langgar dah. Tadi dah langgar dah ada energy loss kan, because due to the friction, and because of that you will create heat, you will generate a heat, and this heat can be transferred outside or inside. Okay, you also will against the law, no heat transfer. And normally in a pipe, okay, because you have this friction or whatever, in industry mostly we put anything that can help the flow whether it's a pump or compressor, okay, to make sure the flow is moving as you wish, okay, because you have this friction, you want to helps the flow, you put this mechanical device. That means you are also against the second law, which is this shouldn't be any mechanical device, but normally we put a mechanical device. Okay, so that's the limitations of Bernoulli equation. Okay, so in theory, okay, that's why we assume the fluid is incompressible. There's no mechanical device. There's no heat transfer. There's no there's no energy loss. Okay, but in reality, they always be there. So in reality, people will calculate lah. Okay, what is the energy loss, and they will add this term, the rest, the energy loss due to friction. Okay, the energy transfer, they will take this into consideration lah. Okay, but in study, when we study about Bernoulli, we assume this so that we can then we can use all this energy balance, the mass balance, energy balance, then we can apply this. Okay, right? what else I miss? Okay, one more thing before I forgot. So this Bernoulli equation, okay, let's me write that's pada mana Allah. Potong dulu. Okay. Okay. Semua boleh. Terlupa lah semua ini. Okay, mana pun. Okay. So this equation, Bernoulli equation, can also be write as, normally we write as P1 plus Z. No, not Z. Pada dulu. Okay, P1 plus rho G Z1 plus rho V1 squared over 2 equals to P2 plus rho G Z2. Let me put them in. Okay, plus rho G Z2 plus last term is rho V2 squared over 2. Can you notify what's the difference between this and this? Apa beza dia?
Tak ada E.
Tak ada E? Mana ada E kat situ? Yang first tak ada E juga. E mana awak cakap? Ni, yang ni dengan
Specific weight sir.
There's a wait, P.
ni ada P. Ni pressure.
Then
Tu apa Roji.
Rho G.
So
DCT.
this term, if you multiply by rho G, okay, that's why you only left with P1 kan? So you can say kan? And that's why you Z1 is you have rho G Z1, and for kinetic energy you have rho V1 squared over 2. Similarly, like for the second point, the point number 2, you will have pressure at point 2, okay, plus the rho G Z2 plus rho V squared, rho V2 squared over 2. So you multiply this by rho G. Okay, and we give you this Bernoulli equation in terms of this. Alright. Okay. So we finish this. Okay, let's look example so that we can see how we can use the continuity of mass balance or energy balance in any problem. Okay, let's say they gave you a pipe like this. Tadi straight je, ni ada elevation okay. So they mention to you this is point A and this is point B, and they give you the height, okay, is 2 meter. Okay, so we assume all the limitations ni lah in place. There's no energy loss, there's a compressible fluid, there's no heat transfer, whatever apa semua tu. Okay, now they give you the area for at this point. Okay, the area, the A1 is equal to 0.2 meter squared, and they give you the velocity at point 1 is equal to 3 millimeter per second. Okay, and they give you as well the pressure. The pressure at point 1 is equal to 345 kilopascal. Okay, and they provide you with the area at point B. Okay, let's say this number 2 last time, so that we are consistent. So this 1, that's 2. Okay, so the area 2 is smaller than this, so it should be 0.1 meter square. And then they ask you, they didn't give you the velocity at point 2, it's not mentioned, and they also don't give you the pressure too, it's not mentioned here. Okay, now they ask you to calculate the P2. Okay, the question is calculate P2. Okay, how we do this?
Find the V first.
Okay, how you find the V? Using what equation?
A1 V1 equal to A2 V2.
Yes. So that's the continuity of equation. The Q tu kan? Q1 is equal to Q2. Okay, and this is equal to A1 B1 equal to A2 B2. So this is very straightforward. Okay, they don't ask you to find V2 pun, tapi you need this V2 when you want to find the P2 kan? So your V2 is equal to A1 B1 over A2. So what's the number? A1 0.2, V1 3, so 0.6 divided by 0.1. Jadinya 0.6 bagi 0.1 apa? 6 eh?
36.
Ha?
36 ya.
36. Ya ke?
Yes.
36 millimeter per second. A 0.2 kan? V 3. So 0.2 kali 3 bagi 0.1. 36 aja pada. Ke 6? 6 lah saya rasa. 0.6 divided by 0.1. 6 kan? Hello?
6 sir. 6.
Saya dapat 36 ni. Ni 0.2, A1 0.2 kan? A1 0.2 meter square. Okay. 0.2 lah, 0.2 times 3 divided by 0.1 should give you 6 lah.
6.
Okay.
Saya silap area tu.
Apa? Square 0.2.
Tak. Saya buat 1.2. Ingat 1.2
Oh, okay. Sorry. This is 0.2 0.2. Okay. So this will give you 6 meter per second. Okay. As the area is smaller, then it should the velocity should be higher lah. Okay. Okay, that's settled for V2. And then how you can find your P2? What formula you can use?
Bernoulli equation.
Okay, good. Bernoulli equation. So the equation is apa Bernoulli equation? P1 over
Specific gravity.
Specific gravity.
Specific weight.
Oh, okay.
Density
Ni
G.
ambil rho G lah, rho G Ambil ni yang this Bernoulli equation. Boleh juga specific weight, tapi tak bagi kan. So we use rho G lah. Correct? Betul? This equation
Yes.
Okay. So P1 over rho G, okay, plus Z1 okay, plus V1 squared over 2G equal to at the point 2, so pressure at point 2, pressure at point 2 over rho G plus Z2, okay, plus V2 squared over 2G. Okay, now they provide you the pressure at point 1, that's good. They also provide you the Z1, they provide you the V1, and this one they don't give you, they ask you to find. And you know the Z2, okay, Z2, they give you Z2 because this elevation is true. Okay, that means if you take your Z1 is 0, oh boh, padam. Alamak, tulis balik. Macam mana nak undo? Tak boleh undo pun. That's good. Kan? Alamak. Saya dah malas tulis balik lah. Apa saya tulis balik lah. Okay, again tadi beli question. Okay, sorry So P1 over rho G plus Z1 plus V1 squared over 2G 2, okay, is equal to P2 rho G plus Z2 plus V2 squared over 2G. Okay, so they give you the P1, as I can kalau okay tadi. Okay, they give you P1 tadi 345 kilopascal So this is the height is 2 meter. Okay, so your Z1 must be 0 lah. If they give you only 2 meter panjang dia, so one reference point must be is equal to 0, and your high elevation point is 2 lah kat sini. Okay, so Z1, you have your Z1, you have your V1. I think the question they give you the V1 is equal to 3, okay, and they want you to find the P2, okay, Z2, you have Z2 is 2, and you also have find your V2 tadi V2 sama dengan 6 meter per second. So you have everything, so you can find your P2 lah. Betul tak? Okay, you just rearranging lah this equation. Okay, don't be jangan buat mistake arranging equation ni kan. So if you take P2 outside, okay, it will give you P1 over rho G, okay, this in bracket, okay, P1 over rho G plus, okay, you have Z1 and then Z2, okay, plus you have you have V1 squared minus V2 squared over 2G, and these all terms must times by rho G. Betul? Betul Okay, then you can just put your value lah. Okay, P1 is 345 kilopascal, so that means you have to times by 1000 divide by rho G. Okay, rho they give you the rho as it's water, so it's 1000 times 9.81. Okay, plus okay, 0 minus 2. Okay, Z1 is 0, so that's your reference point. Plus you have your V1 is equal to 3 squared, and you'll find your V2 is 6 squared. Then you 6, so 6 squared. Okay, divide by 2 times 9.81. Okay, and this all times by rho G. For you take P2 outside. Okay? So if you calculate this correctly in your calculator, it should give you the answer, which is 311,880. What's the unit? Anyone? Apa unit dia? P2 pressure?
kilopascal.
No, I have changed this.
Pascal.
Yes. So Pascal lah. We always use the in standard unit. Okay, they give you the P1 345 kilopascal. So or you want to change it in Pascal, you have to divide by lah 311.8 kilopascal. Okay, if you can see this the pressure at point 1 is higher than pressure at point P kan. Ni 311 kan. Tadi yang P1 tu dia bagi P1 is equal to 345 kan. Okay, that's the Bernoulli equation lah kan. Whenever you have a point whenever the velocity is higher, then you will create the lower pressure kan. If you realize the pressure at point 1 is 345 and the velocity is 3 kan, and point 2 you have calculated it, the answer is 311. That's because the V2 is 6 kan. So this is Bernoulli lah, your understanding of Bernoulli kan. Whenever you blow a paper on a flat surface, the paper will go up kan. Macam kalau tengok Mr. Bean tu, if you blow the paper will go up because you create a different in pressure. You blow a very high velocity on top of the paper, and that's why the pressure is reduced at the bottom. That's why it create the paper goes up so there's a push goes up okay, the pressure, this velocity at the top of the paper is higher, then it will create a very low pressure, and at the bottom of the paper is very high pressure. That's why the paper will goes up. That's Bernoulli lah. Okay, that's about Bernoulli kan. Macam kereta Formula 1 kan, they have a very aerodynamic shape. Why? Because of Bernoulli lah. They want to make sure the car is stable and not fly kan. Goes up whenever the velocity of the air is higher at that point. Okay, now dah habis dah. Okay, I think that's example. There's a lot of example in this slide. I will post the slide in the classroom, and there's a lot as well example in the notes in the classroom. I post the notes. In that notes there are a lot of example you can do. Okay, I suggest you to do it so that you understand how you can understand the continuity equation, Bernoulli equation. Okay, any question before we end our session today? Okay.
Sir. Sir ada share ke slide tu dekat Google Classroom?
Belum. Nanti saya share.
Belum okay.
So this slide I will share in the classroom. But like I said, in the notes there are a lot of questions as well, so you can do in the notes. And all in this slide, everything is based on the notes lah. Okay, I just want to write it so that we can have interactive session lah. That's all. Okay, anything?
No sir.
Tak ada?
No sir.
Okay, wish you all the best for your tomorrow's quiz, chapter 1 and chapter 2. So please be prepared. I'm not sure what to expect, but just if you prepare your best, then it should be not a problem lah. Okay. Okay, that's all for today. I think we already have finished our time. Okay, thank you for your attention and your involvement in the class. I appreciate it. Please fill up the attendance form, okay, through the link. Don't forget to fill up the attendance form, okay, so that I have a record. Let me copy and paste again. Okay, check your chat box. There's a link to your attendance form, and we shall meet again on Tuesday. Okay, and then Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam, sir.